Okay. So yes,
So, madam, can you hear me?
yes, I can hear you.
May I use the washroom real quick? I need to use the washroom. Is it okay? Like for a
Okay.
little bit. Thank you.
Okay. Hmm. Okay. All right. What do I want to say today? So, okay, the password for today's class will be um syukur. Okay. I'll give you a few minutes to fill in the attendance. Aiman, where's your camera?
Sorry, madam. I am using mobile data for the moment because my internet broke down. So,
Internet broke down. Why your internet broke down?
I don't know. Renovation at my place. It take a week.
Okay. The password is syukur. Finish? Everybody? Okay, so finish. Let's continue. Who remembers where we stopped last time?
We stop at Fermi level, madam. And there are few questions that madam remind.
Sorry?
There are few questions that madam want me to remind you.
Okay, what are they?
Direct and indirect semiconductor. Band gap versus lattice constant graph. Effect of temperature to the carriers. And talk about defect in semiconductor. Mechanical stress or strain.
Mm.
Quantum well and quantum dot. Heterostructure, homostructure, heterojunction, homojunction, generation recombination. That's it.
Okay, thank you, brother. Okay, let's start with direct and indirect band gap. Who knows what is it? Anybody?
So the direct band gap is the minimum of covalent bond. The minimum of covalent bond is directly on top of the maximum of valence bond.
Bond ke band, aku ni asyik tukar je lah.
Band. Covalent band
Geng
and
Maisarah ni, bond dengan band tukar macam ni. So, bond dengan band tu two different things, right?
sorry, madam.
So what is the significance of direct and indirect band gap? What's the significance?
Between indirect and indirect.
Electron and holes.
Apa, Rahimi?
Electron and holes.
Tak faham. So what's the significance? How does that relate to the direct and indirect?
Direct. Just like
U and U, electron and holes in straight line, indirect electron holes not in straight line.
So what's the significance of what? So what if it's straight line ke tak straight line? Who cares?
Can
Hmm?
no. Wait.
Okay, direct and indirect band gap is actually very important. This has a very significant impact. I will tell you why. Number one, before that, let's talk about what is direct and indirect band gap. So remember last time we drew the band gap like this, and then we draw it like this: conduction band, valence band, intrinsic, extrinsic. The band gap is always the same like this. The difference is only on the Fermi level. Okay, now, so all semiconductor material will draw it like this, the band gap. Okay, however, actually, this drawing or of the band gap is very what do you call it? It's actually a simplistic a simplistic representation of the energy band diagram. If you look at actually the real energy band diagram, it looks like this. Apa masalah ni asyik masuk keluar, so internet tu cute. Let's say if I try to Google for you, I will show you. The real actually how does the band gap looks like if you do an experiment and you calculate them, and how does the band gap looks like. Okay, it doesn't look like that. It looks like the real band gap. It is a good one. This is difficult to see. Yeah, it looks like, you know, macam apa, bekas telur tu. You know, yeah, the one you go buy like a lot of eggs, where it holds the eggs. It looks something like that. So I'm trying to find a photo that maybe there's not. I couldn't find something that boleh lah. Okay, like this. Okay, let me show it to you. Can you see? So, this one. How do I make this photo big? Okay. Okay, so you cannot see the whole thing. How do I make it smaller? I cannot make it smaller. Okay, maybe if I go back here. Okay, can you see here? This is energy band diagram, the actual energy band diagram. This is energy decay diagram. So you can see it's not straight. It has like a curve up, curve down, and there are multiple levels. The band structure is not like just one band. The one that we are drawing, and inshallah we're using throughout the course, is actually a very simplified one. So two paling simple lah, the most simplified one. If you go higher, you will do master's, PhD, or you do further research very detailed on semiconductor, you actually realize there are many different bands inside the semiconductor. So, but the one that we draw, okay, the simplified version, we just take the hujung ni, the end over here, this end and this end, we just draw like that. And this one also, so you can see here. So if you look at all this what do you call it, this curve, the energy band curve, you have the minimum, you have many here, but there will be always the minimum over here, and there are many here, there will always be a maximum over here. So what we are drawing in our, the one that you will draw the straight line, is actually the minimum of the conduction band versus the maximum of the valence band. So these two end, and will make a straight line like that. Macam tu. We like zoom in and make it straight line. So we don't care about the rest because it's not significant at a normal situation. But if it's not normal, then the this this other band will be will have impact. But normally the most important is the band edge over here, the minimum and the maximum. So here also the minimum and the maximum. So now so this is the real energy band diagram. So what does direct indirect band gap means? So if you look here, you will see the minimum of the conduction band here is aligned directly with the maximum of the valence band. So if you look, if you see something like this, you know this is called direct band gap. Okay, direct band gap, because the minimum of the conduction band align with the maximum of the valence band. So if we try to find something, how does a indirect band gap looks like? It will look like let me draw. So we look like, so if it's indirect band gap, you have like this, for example, and you have like this, something like that. Okay, so where the where the minimum of the conduction band is not exactly aligned with the maximum of the valence band. Okay, so that's so if I ask you to draw the direct and indirect band gap, it looks like this. This is the simplified version. So direct band gap will look like this. Okay, so the band gap. So where's the band gap? So the energy band gap is this between the minimum and maximum. So this is the band gap. So you can see for the direct band gap, so this the minimum coincide with the maximum of the valence band. And for the indirect band gap, the minimum is indirectly coinciding with the valence band. Okay, so but okay, no, but when we draw the devices later on, we don't draw it like this. If it's direct or indirect band gap, it will still look like this. We just take the we just extrapolate. So in the end, we just take this part. Okay, so how do we know whether it's direct or indirect band gap? From the drawing here, we cannot know. We will never know if I give you a drawing like this. From this drawing, you don't know whether it's direct or indirect band gap. So how would you know? Is by looking at the material. So that you need to like Google or find a journal or book of the material. You can there's like a table, you can check whether it's actually direct or indirect band gap. So what is the significance? So who cares, right? Whether it's direct or indirect band gap. It's actually very important. Why? Now we talk about recombination. Mana orang Kuantan tak ada hari ni? Ada orang Kuantan ke hari ni? Mana ni yang penting dia duk buat research tu? Tak datang pula hari ni. Tak apa, dia dah datang. Kita tanya dia kau next class. Okay, so now we want to so what's the significance? In order to explain you about the significance, we talk about recombination. For us to talk about recombination, we need to talk about generation. Ni like adik-beradik, brothers and sisters. Generation and recombination. So what are they? Okay, now, so just hold your thoughts about this. We'll go back to this later. So now, biasanya, normally we say generation recombination. It's not the other way around. Okay, generation and recombination. Okay, so let me draw my energy band diagram. Okay, so this is my energy band diagram. When you have excitation, you still remember, right? How do we get free carriers? In order for us to get free carriers, we excite the electron from the valence band to the conduction band. Okay, we call it excitation. The other name of it is generation. Generation of free carriers. Nampak dia nama generation because it's generate free carriers. It's called this process called generation. Okay, so generation. Okay, generation can, so this type of generation we call it the band to band generation. Why the name is like that? Because it's generating from band to band. So from valence band to conduction band. So it's called band to band generation. Is there any other type of generation? Yes. There's another type of generation which involves defect. So after this, we talk about defect. How? So satu-satu one by one. So now we talk about band to band generation. Basically, now I want to teach you generation. Generation is a generation of free carriers. Whenever a process where you get free carriers is called generation. So what is recombination? Recombination is the opposite. Is the opposite process of generation. So it's a process of losing free carriers. Okay, so it's a process of losing free carriers. Okay, so here, this process here, by electron exciting to the exciting to the conduction band, you have free electrons over here. Here, the free electron will recombine and it will go to the valence band. You know, whenever an electron goes to the valence band, it means it becomes bound again. It cannot move. When it cannot move, we say we lose free carriers. It is no longer free. So we call this band to band recombination. Now, so what's the significance, right? So okay, electron. Electron are like us human being. If I ask you, if you stay on Earth, not as a flat land now, or like a normal flat land, and you go to Mount Everest, you go to the top of the Mount Everest. So where do you like to stay? Is it in the top of Mount Everest or in the top on the floor, the flat Earth? Which one do you prefer to stay, Rahimi or Ahmad or anybody?
Flat random.
Yes, why? Because it's the lowest energy. You feel safe, right?
Correct.
Because it's the lowest energy. So electron the same. Electron always want to go to the lowest energy. It doesn't feel comfortable being at higher energy. So that's why we have to generate, we have to push the electron to go to conduction band. So we give energy for it to go there. But if there is any chance the electron can choose or have any opportunity, the electron wants to go back to the lowest level, which is the valence band, and this process is called recombination. Okay, but the process of recombination, we will lose free carriers. Okay, so that's the thing, we will lose free carriers. So that's why we need to understand this, so that we need to, it depends on the application, what you want to do with your semiconductor device. Some devices we want generation, some devices we want recombination. Okay, later on we'll talk about this, but these are two fundamental processes that you need to understand: generation and recombination, okay, of electron. So does the hole also go through this process? What do you think? Hole?
I think so, yeah.
Yeah, so hole also, just like electron, his friend, they are both brothers and sisters as well. So electron like to generate, of course, hole also like to generate. So but the how hole generate is the opposite direction. How a hole recombine is the opposite direction. Okay, all right. So you can have hole generation, electron generation, hole recombination, and electron recombination. Okay, any question up to here?
I have a quick question, madam. So recombination happens when there's no more excitation or there's no energy, right?
No more energy, no more energy, no more energy.
Like I give heat to the element, for example, and then when I remove when I take away the heat, recombination happens or no?
Okay. Okay, good question. There is a probability. So when we talk about semiconductor, because there are lots of electron holes, like millions of it, right? So normally, we as an engineer or scientist, we talk about the probability of generation and probability of recombination. So when you apply heat or you increase the temperature, the probability for generation is very high. But they will also the higher than no heat. So recombination, where there's no, you didn't apply any energy, there's higher probability that it will recombine. Okay, there's a higher probability that it will recombine. However, so whenever first, before it can recombine, generation need to happen, right? So you need to have electron over here first, in the first place. Otherwise, there's no recombination. So after if the electron over there goes over there, the electron can. So what happens to the electron? What the electron do? Electron will move here, move there, until it found a pair where it found like a where it can recombine. It's like when recombination is actually occurring when a free electron meets a free hole. Okay, when electron move, hole move. So if I draw it like this in terms of energy band diagram, kalau kita if we draw it like this in terms of the physical, electron moving around, like it will go move here, go there, and then here hole also move here, move around, free hole, free electron, right? So when both meets, bang, recombination happens. So the electron needs to meet a free hole in order for recombination to happen. But generally, it will it will meet, but some of them will move and will not meet. So some of them will keep will just move randomly here and there. And then it will recombine, generate again, recombine, generate again. So some of the electron will recombine, and then because of the heat, it will. So this process keep on going. Okay. All right. So that's why. So this at room temperature, generation and recombination process will keep on going. But when we design a device, we need to smartly think, how do we increase generation and how do we decrease or we increase recombination based on the device, which one we want. So but these both processes will keep on occurring at room temperature. Okay. Any other question? Okay, no question. Okay, if no question, we'll continue with generation, recombination. You know what is it? Okay, now generation, you take energy, right? So in order for you to generate, this electron must gain energy, right? And I told you before how this electron can gain energy. We talked about before, right? In one of the class, we talk about you can generate, you can give the energy to the electron here through heating, to temperature,
Radiation.
to radiation, through shining light. Also, you can shine another light with a higher band gap, then this will be absorbed by the electron. So generation, so as I said, excitation generation is the same thing. So it takes energy, it gains energy. But this process, recombination process, is the opposite of generation. It means that whenever we have recombination, it releases energy. Okay, let's write down. So recombination release energy, and how much energy it releases is the energy of the band gap. So here the same, if you want to generate the electron, the minimum energy that the electron needs to get is the band gap energy. And here, when recombination occur, okay, when you have recombination, this process will release energy, and the amount of energy is the energy of the band gap. Okay, clear? Now, so how does that relate to direct and indirect band gap? Okay, so right here, direct band gap material recombinate. So now we talk about recombination of the combination indirect and indirect band gap material. For the direct band gap material, whenever so if an electron recombine with the hole over here, what happens is it will release energy. So it will release energy, and this energy is in terms of phonon. Phonon, kau dah silap. Photon. And then this indirect band gap, if it's recombined with, so direct band gaps is easy, that it will it will go directly like this if it's recombined. But for indirect band gap, what happens is if there's recombination, it will go two ways. So we'll go two ways. So this is, I forgot to tell you, this is energy and this is momentum. This is the axis is energy, this axis is momentum. So if for a direct band gap material, when there is any recombination occurring, the momentum doesn't change. So direct only release of energy, there's no change of momentum. But for indirect band gap energy, when there is a recombination, there will be change of momentum. It has to go to here to go there. Okay, and the consequence is, if this indirect band gap, if you have recombination, it will release energy as well, but the energy in terms of phonon. Who knows the difference? What is photon and what's phonon? Anybody knows? Proton, phonon, photon. Don't get confused. So I know, so sometimes students can get confused. I will tell you, proton, you know, so you know what is proton, what is hole. So do not confuse between the two. Now we have photon and we have phonon. Photon is actually light, L-I-G-H-T. Photon is light in terms of particle. So you learn in your A-level, O-level, SPM, light can be two types, right? Light, you can view light as a wave, right? So, but light can also behave like a particle, right? So whenever light behaves like a particle, we call it photon. Okay, we call it photon. So so that's photon. So basically what happens is, so this is very important, when for direct band gap material, if there's recombination, the output is always light. Okay, so you get light coming out, which is great. Okay, this is how you get LED, how you get laser. You have recombination, you have light coming out, great. But for indirect band gap material, if you have recombination, it will also release energy, but not in terms of light, because there's a change in momentum here. In terms of phonon, phonon is is heat, in a heat particle, HEAT, heat particle. So indirect band gap recombination release heat, direct band gap material release light. So this is very important. So when you want to design any device, if it's something that gives out light, you need to choose material which are direct band gap. Okay, how do you know? As I mentioned, people need to do experiment, you need to do some like complicated equation, but for us engineers, very easy. We just open a table, you can open many journal, book, internet. If you type the material, they will tell you whether it's direct or band gap, direct or indirect band gap. There's a lot in the book. So from there, you choose which one is suitable for your application. Okay, any question up to here? No. Okay, good. Okay, now we talk about direct.
Prof, saya nak tanya, Prof.
Hmm.
Kalau untuk indirect band gap tu, macam mana dia
Can
boleh
you speak in
decide
English, because we have
sorry.
international friends here.
For the indirect band gap, how do we decide it will emit phonon or photon? I mean like how phonon get emitted for the indirect, why it's not photon?
Okay, I think I answered just now. Anybody else? Anybody wants to try to answer Amirul's question?
Change of momentum.
So if change in momentum, it means that the momentum is still conserved or not conserved? Yeah, because the EK diagram, because we have like in different value of K, right?
Yes. It will
So
change so that no conservation of momentum. No.
oh, so the momentum is not conserved.
I don't know. I can't. You need to check. I don't know whether the right word conserve or not, but there's a change in momentum.
Oh, okay.
I think you should conserve at all moment, but there is change of momentum here.
Okay.
No change of momentum here. There's a change in momentum.
Okay.
Okay. Any more question? No. Okay. Now Kita apa lagi kita kena belajar, Iman? Defect. Defect. Okay, let's go for
Defect.
okay, what is defect? What is defect? My Sarah?
A flaws in any process or something broken. It's a flaws.
Okay. What is defect in semiconductor? My Sarah?
Defect in semiconductor might be determined through the how many electron succeed to recombine through the with the holes on the valence band. For me, that's a defect. I'm sorry, it's not accurate.
It's not even accurate, it's wrong. Okay. So, okay, anybody else want to try what is defect in semiconductor? If you have to Google, you Google, you answer me.
Defect in semiconductor, there is a loss of atom in the lattice constant.
Loss of what?
Atom.
Loss of atom in lattice constant. Lattice constant? You sure?
Yeah.
Okay, that's okay. Lepas ni kita belajar pula apa benda lattice. Okay. Thank you for bringing that up. So we won't learn about defect first. Let's learn about lattice or lattice constant. What is lattice? What is lattice constant? Try to Google now. Huh? Yeah.
Meaning
Yes, Masara.
the arrangement of an atom. So when if lattice constant means the arrangement of atom has its own distance or constant.
Do you agree, Aiman?
For lattice, I agree. For lattice constant, I think that there is a distance between each atom.
Tak sama dengan Masara jawab ke?
Dia macam ayat dia macam susah nak faham.
Okay. So brothers and sisters, so what is a lattice? So you should know about lattice, but later on we'll talk about the process called lattice scattering. So if we talk about like now we are in kindergarten level, we want to go like another level, so we need to know kindergarten level, right? So what is lattice? Lattice is regular arrangement of the atoms in the material. So this is lattice. So the black dots over here are the atoms, right? So this is lattice. Okay, lattice constant. So this whole thing is lattice. The lattice constant is the distance between the atoms. Okay, the distance between the atoms, and normally the unit is angstrom. So what is angstrom? Angstrom is 1 × 10⁻⁻10 meter. Okay, so lattice constant is the distance between atom to atom. Is it important to know? What do you think? Siapa yang tak nak cakap lagi ni? Today who are very quiet. Faris. Do you think it's important the lattice constant, to know the lattice constant?
But yes.
Why?
To fit into is the calculation.
Huh?
The calculation
I can hear you.
to is the calculation.
Compilation.
Calculation.
Calculation.
Yes, calculation.
Calculation for what?
Calculation.
I don't know that, madam. First time I hear about lattice constant. Maybe it's important, maybe it's not. But since madam are teaching it, my guess is it must be important, right? That's why you say it's important. Okay, lattice constant is very important. Why? It relates. It has to do with defects. Okay, how does that? So now you understand what is lattice and lattice constant. Aiman punya statement just now. What is defect, Aiman? I already.
Loss of atom.
That's not the full sentence you said just now.
Defect is the loss of atom in lattice constant.
Is that right? The statement? You think of the statement? Does it make sense?
Oh, the
Anna?
loss of atom in lattice.
Yes.
Yeah.
Not lattice constant. So now, since now you know already lattice and lattice constant, need to be careful in the exam. If you answer like that, I would say that I give 0 straight away. It shows that it's not that the answer is not accurate. It shows that you don't understand the difference between lattice and lattice constant. So in semiconductor, whenever you write something, it's not that we are not talking about accurate or not accurate. It can be wrong because you don't understand what lattice constant means. So be careful. I'm warning you again and again in this, when you write in the quiz, be careful of think exactly what's the word, because it can mean something else. So lattice something else, lattice constant something else. It's two different things. Lattice constant is the distance. Lattice is the whole arrangement. So if you say lattice constant is lattice, it shows that you don't understand. Then why should I give you pass my course, or if anybody makes it? You understand? So that's my thinking. So say it's the same, madam. No, it's not the same. Okay, it's not the same. If it's the same, if you think you're the same, we are the whole Intel will corrupt, because nothing of the semiconductor can be made properly if you don't be accurate and know what is which. Okay, so now good. So now we know what's lattice constant. Now we want to know defect. Defect, like what my Sarah was saying, defect is something which is not ideal. Anything which is not ideal in the lattice structure. Okay, this is the lattice structure in the semiconductor device material. So now still we talk about semiconductor material. In the semiconductor material, whenever anything which is not ideal to the structure is called a defect. Okay, so there are many types of defects. Okay, if you go and read textbook, or you go and read Google defects in semiconductor, you see many types of defects. So, but here we'll be learning only like a few. I'll just give you some example, like famous examples, so that at least you know what is a defect when people talk. It's not it's beyond this course to know everything. If you want to know everything, you go to another course. Okay. But here we just introduction to defect. So what is a defect? For example, here, let's look at our lattice here still. I draw it bigger. So this is our lattice. So very nice. This is very nice regular lattice, no defect. So say during the growth of the semiconductor, we call it growth. During the growth of semiconductor, why we call it growth? Because okay, sometimes we call growth in silicon. Sometimes silicon technology they call it fabrication. but fabrication actually means it's more specific, not only the growth. Fabrication can also mean growth. Fabrication can also means that you put contact, you put metal contact to it. That's also called fabrication. But growth is just the semiconductor material. Fabrication, the material can be you grow the material plus you add contacts to it. Okay. So for the purpose of this class, we just call growth. Growth is just the semiconductor alone. We don't talk about the contact yet. No, just the semiconductor. So the growth, why we call it growth? Because now I want to introduce you to another term. We call it epitaxial layer. Okay. Oh, apa ni bunyi macam pelik. Okay, epitaxial layer is just means that layers of semiconductor. So whenever you need to imagine how do we make this semiconductor material? How do we design it as an engineer? How do we make it p-type, n-type? How do we do that? So normally you have like a big chamber, right? And then you put gas. So in this chamber, there are high pressure, high temperature, and then there's inlet of gas. And the gas, for example, you want to make gallium arsenide. For example, you want to make the material gallium arsenide. So what happens is you have a piece of gallium over here, right? The piece of gallium. Oh, bukan, no, that's wrong. That's not right. So basically you have a substrate over here. Substrate can be anything. Substrate, do you know what substrate? Substrate basically the base. If you want to make a cheesecake, right? Have you ever made a cheesecake? So after this, go and see how people make cheesecake or you do cheesecake. So if you make cheesecake, you need to have the bottom crumbs, right? And that is the substrate. Okay. So then we have the substrate. Now we want to, on top of the substrate, we want to build the semiconductor material or layer. So you put the gas of gallium here, the gas of arsenic here, and very high temperature, it will mix and it will dia akan be apa nama ni, collected here. So the more gas you put, the thicker it will be. Okay. And this process we call the growth. We grow the semiconductor. Okay, so that's how, for example, indium gallium nitride. How do you make indium gallium nitride? Indium gallium nitride is a semiconductor. So the same, we have three gas. Okay, so you have the gas of indium gallium nitride. Put the gas. So how much percentage of indium? You increase the gas of indium, right? And if you increase the gas of indium, the percentage of indium will be higher. Then therefore you get a different composition. Okay, and this process is called the growth. And what is epitaxial layer? This is epitaxial layer. We grow layer by layer. Okay. And this we grow this layer by layer. You can imagine like kuih lapis. You know, cheesecake. I like food. That's why my example are all food. I'm sorry for that. So jadi you know kuih lapis, Ahmad? Have you eaten kuih lapis before?
It's like jelly, or am I wrong?
It's like jelly, yes, jelly, but with many layers, right? You can peel off.
Yes, I've had it. Yeah, I've had it.
Yeah. So the growth of this semiconductor is like kuih lapis. The making of kuih lapis. Have you ever made kuih lapis, everybody?
Never.
Never. Hana tak pernah. Hana, we need to be proud of our Malay food and culture. You know, I tried my first.
Pernah lah tapi tak jadi.
Tak jadi lah. Yeah, why
Tak jadi.
why did tak jadi?
I used the wrong bahan dia silap.
Okay,
So
so
tak jadi.
there's a good example of semiconductor can be as like that as well, tak jadi. Why? Semiconductor is a more complicated than kuih lapis. If kuih lapis pun tak jadi, how are we going to make semiconductor layer? So semiconductor layers are more complicated compared to kuih lapis because the temperature, the pressure sometimes you need to play with the temperature and pressure because each gas over here, they are very sensitive to temperature and pressure. So sometimes you can increase, decrease. So sometimes the semiconductor doesn't become kuih lapis that we want. Okay, so I tried my first time make kuih lapis when I was in UK. My husband really wants to eat kuih lapis. After 3 years, we haven't eaten kuih lapis. Okay, I said okay lah, I'll be a good wife and try to make kuih lapis. First time in my life. So I tried, how just like this piece, this big, only this piece, very small piece. It took me 1 day. Can you imagine? From morning until night, crazy. So it's like, after that I said to my husband, I'm sorry, I will never do this for the entire of my life. I will never, because I had to like, so difficult. So you have to put 1 layer, put another layer. And sometimes if the composition is not good, it doesn't become like very nice like jelly like, it becomes like porridge. Okay, it becomes like, and then not only that, so let's say you make it nice, you'll be waiting for 3-4 hours. It may look like layers, but there are bumps on the layers, right? It's not as smooth, and the bumps is what we call defects. Okay, the bumps are the defects of our semiconductor or our kuih lapis. So here, so going back to our here, so we make these layers, but because of due to some we cannot accurately control the temperature or the pressure, or there's something, or there will be an impurity somehow. This chamber is contaminated by a very small dirt or something. Then it will land on this semiconductor material, and it will create defects. So there are many types of defects. Okay, so now you understand what epitaxial layer is. You know what is a substrate. You know this process of growth. Now defects. So there are many types of defects. I said you can have defects. For example, if there's no kuih lapis at all, like means there's no semiconductor material. But sometimes you will get the layer, but that you see imperfections in the layer. For example, I say bumps. So for now, for example, in our lattice here, so a good semiconductor material have a very orderly arranged lattice. Everything nice, everything perfect. But because if I say this so difficult, tricky to grow this material, you might get defects. Sometimes slight imperfection. One of the defect that you can have is you lose one atom. Sometimes the bond it doesn't fall nicely. Okay, when it doesn't fall nicely, you will lose an atom, and this is called a, you know what this defect is called? Nama dia vacancy. Vacancy defects. Okay, so there are many defects. So this, even losing one atom, you have millions, billions of atoms in semiconductor, right? You lose one atom is not at its place, is already a defect. And physically, if you look in AFM or TM, atomic force microscope, not a normal microscope, it's a very expensive microscope. Previously in our material engineering, we have this microscope, but it got broken and then so expensive to maintain it. So now it's not working anymore. Very sad. We don't have money to do semiconductor research. Is very expensive. To do semiconductor, anything on semiconductor is actually very expensive. That's why only the rich countries who have this semiconductor technology. You know which country, because it's very expensive, not any country can build this factory of semiconductor, because the capital it takes billions of ringgit and dollar to build a factory. That's why normally like Intel, Infineon, if you look at the map after you Google which country have factory of Intel and Infineon on this, number one, they will choose a stable country. They will not do it in Syria, Jordan, Palestine, whatever, the Muslim countries, most of it. They will not invest over there because it's not stable. Anytime you can have war, and then all bomb habis billions of US dollar. So they will invest countries which are stable. Okay. China have it. So because China is stable, because they after China open it, number one, stable. The most important is stability. Number two is cheap labor. There are two things. So that's why Intel, most of it are not in US nowadays. They have their outlets, their factories, the what do you call it, the fabrication in US, but mostly now throughout the world, because the labor in US is expensive. But they are very smart. They are based. It's a US company. Their headquarters are in US. Okay, let me stop. How do I post recording? Did I record just now? Oh yeah. Zoom. So I will share you. So this is not a simple thing lah. This is so it's important for us to really understand this and get the knowledge on our own. But if you want a job, yes, in Malaysia there's a lot of job on this. So going back to defect, so you have this is called a vacancy defect. Okay, so what another type of defect will be so not only one atom missing, a line of atom missing. So for example, okay, so you can see here there's a line of atom missing. Okay, and this is called, we call it dislocation. We give a name because it's easier, right? So a line it's a defect, but like a line of defect, we call it dislocation. And from the microscope, expensive microscope, if you look at it, you can see there's a like a line missing, because the atoms missing, it looks like a line missing. So we call it dislocation. So using a microscope, we can see with our eyes these defects. So now the question is, how does this defect manifest itself in terms of energy band diagram? Okay, so how does it look like? So because we don't care, okay, if it's a defect but it doesn't affect the electronic properties, we don't care. So if you have defect like this, it looks terrible, it's horrible, you have full pimple but you can still work, so okay lah. So who cares if you tell me semiconductor, your chip is ugly, it's okay, because outside you still have casing and everything. So no problem. So, but the problem is when it looks ugly, defects, you have defects, but it's affecting the electronic properties. And that is when we are concerned. So when it's affecting our energy band diagram. So this defect, what happens is it will manifest. We will translate this defect in terms of energy band diagram. It becomes an energy level inside the band gap. So dia akan jadi macam ni. Nobody will see ET. The trap. Defect and trap is the same. Sometimes we call defect, sometimes we call trap. So these defects inside semiconductor, if it's electronically active, it will manifest itself in terms of energy state inside the band gap. So it can be anywhere. It can be here, it can be here, it can be here, it can be here, it can be anywhere, it can be multiple, many. So it depends on the type of defects, and it depends on how much defect it is, the density of the defects. And we will discuss about the defects, the effect of the defects to the generation and recombination next week, inshallah. So this defect, since it's already in our energy band, and of course it will do something to the process of our electronic process of the current flow of our material. So we'll discuss about what is the defect of this, inshallah, next class. Okay. Any question up till now? Any
No question,
question?
madam.
No question, huh? You all happy, sure?
I have a quick question. It is
Yes.
the defect on the physical appearance is not important, right? The
It's
effect
what?
more the defect on the physical appearance of the semiconductor is not important. It's insignificant, right? It's more to the properties.
Yes, for us, electronic engineers, yes, we don't really care. But generally, if you see if it's ugly, your your face, this is not human being. Your face can be ugly, but your heart is nice. But generally, the semiconductor, if there's defect, you can see it's ugly inside. Also, it will be ugly. It will affect the electronics.
So
Generally.
if there's one atom missing, then the semiconductor is just will be thrown away, right? You just have to make a new one.
No, no. It doesn't. You don't throw it away. I will say so because you cannot get generally in life. Nothing is perfect. Only Allah is perfect. When we grow something, it will not be perfect. You will always have defects. Okay, defect will always be there. In semiconductor. That's why when we say silicon, the purity of silicon, we say 99.9999999%. But still there's 0.00001% that is not impure, right? So nothing is perfect. So also that you will see defect. So we need to live with defects. The only thing is the defect significant or no? The density of the defect, is it significant or no? But there will always be defect. Okay. Okay, all right. So then also we'll discuss next time how do we get, number one, you already know how do you get defect is through how when we grow the semiconductor, you have like you introduce this defect. You can also introduce defect by radiation. Radiation also hit the atom will displace, therefore you create defects also. Okay. Any more question? No? Make sure you understand everything. If you don't understand, you better go read this before you go to another level. I haven't gone in semiconductor device yet. This is all semiconductor material, not yet device. Okay, so that's why, but this is fundamental, is very important. You don't understand this, I will not repeat in the semiconductor device when we talk about semiconductor device. If you don't know, you will drown, you will fail this subject. Okay. All right, I think that's all for now. Let's end with the dua, please.
Wait, no brother's gonna do it?
I don't know, there must be
Okay,
one guy. Okay.
I'll do it. Oh,
Bismillahirrahmanirrahim.
sorry. Go ahead, sorry.
Oh, Aiman, you recited before, Aiman?
No.
Okay. So who? So up to you, Aiman or Ahmad?
Bismillahirrahmanirrahim. Rabbana la tuzigh qulubana ba'da idh hadaytana wa hab lana min ladunka rahmah innaka antal wahhab. Ya Fattahu ya Alim iftah qalbi futuha arifin. Allahumma inni
Inna.
astaudibuka.
So, no, brother, when you said the
Allahumma
inna, because inni means me, inna means we. So you're making dua for yourself or for all of us?
Allahumma inna astaudibuka ma 'allamtanihi
Ana.
fardu.
So there's an Arabic. So it's okay. Let's give to Ahmad next time. Everybody else, check your dua to be for us, not for you only. It's not fair. We say Amin, it's only for you. Okay, Aiman, it's Arabic word. Dia ada nahnu, ana. So ini means me, inna means us, barely us. So you can check Aiman. So you learn something. Okay, Ahmad, you make the dua.
بسم الله الرحمن الرحيم يا حنان يا منان يا بديع السماوات والأرض يا ذا يا ذا الإكرام. اللهم آتنا فهم النبيين وحفظ المرسلين المقربين. اللهم افتح علينا باب رحمتك وانشر علينا خزائن علمك برحمتك يا أرحم الراحمين. صلى الله عليه وسلم محمد وعلى آله وصحبه أجمعين.
Have you recited the dua before? No.
This is my second time.
Okay, not la second time. It has to be first time for everybody first before we go to the second time.
Okay, Islam.
It's okay for today. It's okay. Next time, the rule is you only get once. Okay. You cannot volunteer until finish one round. Okay, that's the rule. Okay, everybody. So and that will force those who haven't recited will recite the dua. And make sure you check the dua for everybody, not only for yourself. Okay, thank you very much. Let's end with tasbih kifara and surat al-asr. Subhanakallahumma wa bihamdika nashhadu an la ilaha illa anta nastaghfiruka wa natubu ilaik. Bismillahirrahmanirrahim wal asr. Innal insana lafi khusr illa alladhina amanu wa amilus solihat wa tawasaw bil haqq wa tawasaw bis sabr. Okay, assalamualaikum warahmatullahi wabarakatuh.
So thank you, madam.
Salam.